Okay, the integral form of the total mass balance equation which we have derived is usually used after making few simplifications. So, we will see how do we simplify this integral mass balance equation. Okay. So, now the general form of the mass balance equation allows us to have any part of the surface as inflow and outflow. That is why it is just integral over the end. When I say integral over control surface, the entire control surface is considered, and wherever there is inflow outflow, that can be accounted for. Now, what we will say, we will write it for a case where there are well defined inlets and outlets. Let us say for this case yeah, these are let us say inlets and these are outlets, and we have also seen earlier a schematic of this where it is a pipe network where we have 2 inlets and then 4 outlets are there. So, let us write this expression which allows for any part of the surface to be inflow and outflow to a case where there are well defined inlets and outlets. Okay. So, let us do that. For the case of illustration, let us take 2 inlets and 2 outlets. So, I split the outlet as CS out 1, CS out 2, and then CS in 1 and then CS in 2. So, what is that I have done? The first term which represents the rate of change of mass within the control volume, that is retained as such. This term which represents the net rate of flow of mass out of the control surface, the control surface has been split into 2 outlets and then 2 inlets. Wherever there is no flow, it is not going to contribute. Okay. Now, let us simplify this further. Now, what we assume is that the velocity is perpendicular to area A. What does it mean? Okay, at this stage, there it allows for any velocity, any angle between the velocity vector and the normal vector. Now, I make a simplification saying that the velocity is perpendicular to area A. What does it mean? Let us say this is the inlet, the velocity is exactly perpendicular to the area A, which means it is along the normal, of course either making 0 degrees or 180 degrees. Similarly, if this is the outlet surface outlet, the velocity is exactly perpendicular to the area, which means it is along the normal. Now, that is what is shown here. So, what happens if it is a outlet is shown here, this is a normal to the outward normal to the surface, and the velocity vector is also along the normal and both are along the same direction. So, theta is 0 degrees. So, V dot n just becomes V, the magnitude of velocity. What is that I have done? V dot n has been represented as magnitude of V, magnitude of n multiplied by cos of the angle between them. This of course is unity, and magnitude of velocity vector is represented by the V scalar. Here V is a vector, here V is a scalar. V represents magnitude of velocity, and then because the velocity vector and the normal to the face are along the same direction, theta is equal to 0 degrees. Okay, so, cos theta is 1. Now, if you take the inlets, okay, we have 2 inlets in this case, what happens? In this case, if you look at this diagram, this is the normal, outward normal, and now this is the velocity vector, this is the velocity vector is perpendicular to the face, but n and the velocity vector are opposite each other. So, theta is 180 degrees for the case of inlet surface. So, once again let us expand V dot n, magnitude of velocity and that of n multiplied by cos of the angle between them. Now, for magnitude of velocity vector I have used V, cos theta is minus 1, of course for the magnitude of n is unity. So, V dot n for outflow becomes equal to V and V dot n for inflow becomes minus V, where V represents the just the velocity, let us say 5 meter per second, 2 meters per second, etc., the magnitude alone. Okay. So, let us use this and simplify the equation which I have written earlier. First term is as such, second term instead of V dot n I write V here, I write V here. Okay. Third term which is for the second outlet, once again write V dot n as V, and then for the first inlet I write V dot n as minus V. Similarly, for the second inlet I write V dot n as minus V. So, difference between this equation and this equation is, or the simplification is that, while the first equation allows for any angle between V and n, here the velocity is perpendicular to the area A, which is the case most of the time. So, a more easy and practical application, practical way of the practical representation of the integral total mass balance equation. Okay. Okay. So, let us proceed further, and when we write as V dot n, it automatically takes care of this sign, but if you write in terms of V, then we ourselves take care of the positive or negative sign, that should be kept in mind. Okay. Okay. Now, let us make another assumption, density is uniform within the control volume. Okay. You have the we have taken a control volume with multiple inlets and outlets. Of course, here you have 6 of them, we have considered only 4 of them, and within the control volume I say the density is uniform within the control volume. Okay. And then I also say that if you take this area, the density and velocity are uniform across this area. So, 2 more assumptions are made, within the control volume, inside the control volume density is uniform, and in this surface area, whatever be the surface area, inlet, outlet, etc., within this surface area the density and velocity are uniform across that. Okay. What is the implication of that? Let us see that how does it get simplified. Okay, the first term, because density is uniform within the control volume, I can take this out of the integral. Okay, it is not varying, and then what we have is integral over dV over the control volume, which gives the volume of the control volume, which is capital V. Okay. So, this term becomes d by dt of rho into V. This was possible because we assumed density to be uniform within the control volume, and I could take out density out of the integral sign. Now, let us take the first surface integral for the first outlet, this particular term. Now, we assumed density and velocity to be uniform across the area. So, I can take out both density and velocity outside the integral sign, and what I have is integral dA, which is nothing but A. Okay. So, rho out 1 V out 1 and integral of dA became A, all the subscript represents this is the first outlet. Okay. Similarly, for the second outlet, and then first inlet and then second inlet, of course, remember we have a negative sign here. Otherwise, conceptually in every term we take out the rho and V out and integral of dA becomes A. So, now this equation is of course looks much more simpler than the integral expression, much more many at times you can use these assumptions. Of course, velocity may not be uniform across the cross section, but otherwise you can usually take density to be uniform within the control volume. So, those assumptions are very, and then velocity perpendicular to the area are usually well known assumptions, well valid assumptions. Velocity may not be uniform across the area, but otherwise you can use this. Okay, fine. Okay. So, let us go ahead. So, the same expression is rewritten here for 2 outlets and 2 inlets, and now we will generalize this for multiple outlets and multiple inlets. We have taken 2 outlets, 2 inlets just for illustration purpose. We can easily generalize that to multiple inlets and multiple outlets. Okay. So, let us do that in the next equation. Okay. So, instead of saying 2 inlets and 2 outlets, restricting ourselves, I say there are n number of outlets. So, I write these 2 terms more generally. I say sigma I equal to 1 to number of outlets, in the earlier case it was 2 outlets, and then rho I, V I, A I. at each outlet there could be a density, there could be a velocity, and there could be of course area as well. Area represents the area of this cross sectional area. Similarly, there could be multiple number of inlets. Remember the minus sign because these Vi represents the magnitude of velocity. So, we have taken care of the negative sign, and once again there could be multiple inlets and you sum over all the inlets with respect to densities and velocities, areas, etc. Okay. Now, we know that V I into A is a volumetric flow rate multiplied by density gives the mass flow rate. So, same expression can be written in terms of mass. Rho into V is of course the mass of the contents of the control volume or mass in the control volume. This equation has been put in terms of mass units here, mass here, mass flow rate here, mass flow rate here. Okay. So, two ways of expressing the same equation. What is the distinction between these two? Usually the variables with which we are interested to express the conservation equations are density, velocity, pressure, which we will come across little later, and then temperature, concentration, etc. So, this equation represents the conservation equation in terms of density, velocity, area, and that is what usually you measure in a plant. Those are the measured variables. If you have a control volume with continuous flow in, flow out, usually you measure the velocity, area is known, density of the fluid stream is known, or you measure it. So, you represent in terms of rho I, V I, V I, A I, but sometimes from a say problem solving point of view, the mass flow rate may be given to you directly, okay? And in a lab experiment you may measure the mass of a sample. So, those cases mass becomes a more measurable value, and those cases or some instruments can give directly the mass flow rate itself. Those cases this equation becomes much more useful, but otherwise this is a more useful and general form the conservation equation in terms of rho the volume, the control volume, velocity, area, etc. Okay. Okay. So, just to summarize what we have done, we started off with this equation, the most general form of the integral total mass balance, and then we have expressed that either in terms of this equation or this equation. Okay. This particular term, rate of change of mass within the control volume, is represented the first term here analogously. Now, this term we said, so not this term represents the net rate of mass leaving the control surface, and that term has been now expressed in terms of these two summations. Now, it becomes very clear from these expressions that this represents the sum of all the outflows, this represents sum of all the inflows. So, when you take the difference between them, it represents the net rate at which mass flow leaves the control surface. So, earlier it was little the meaning was inside the integral, now become based on these assumptions they are very clearly shown that this integral indeed represents net rate at which mass leaves the control surface. Okay. Okay. Now, to understand the integral, this particular integral in different forms comes repeatedly in this course. So, let us understand this in a different way. We are going to arrive at the same meaning, but in a slightly different way. Okay. So, let us start with this V dot n. We have a face, and then the normal to the face is along one direction and the velocity is some other direction. Okay. And V dot n represents the component of velocity along the normal. We know that dot product represents the projection. So, V dot n represents the normal component of velocity along the normal. So, I call it as normal component of velocity. Okay. Now, velocity can be represented as a flux. Let us see how do we do that. Velocity is of course volumetric flow rate divided by area. Volumetric flow rate is volume per time divide by then divide of course area as such. Now, any quantity expressed per unit area per time is called as flux. So, the quantity what we have is volume. So, this term becomes volumetric flux. So, what is that we have shown here? Velocity can be expressed as volumetric flux. So, better to keep this in mind, we will use this few times later as well. Either you can say velocity, which is well known to us as volumetric flow rate by area. Express volumetric flow rate as volume per time, then it becomes a volumetric flux because it is volume per time per area. So, velocity is volumetric flux. Okay. Now, so V dot n is volumetric flux accounting for the normal component of velocity. Okay. Now, rho V dot n is the mass flux because we are multiplying by density. So, this volumetric flux rho V dot n becomes mass flux. Now, when you multiply by a small area dA, it becomes mass flow rate. Why is that? For example, if you see here volume per time per area, when you multiply by area, you let us say mass flux is mass per time, okay, per area, and when you are multiplying by area, what you are left out is mass per time. So, which is mass flow rate. Now, this mass flow rate represents the flow rate over a small region dA. You integrate over the entire control surface and it becomes net mass flow rate, because some regions mass may leave, some regions mass may enter, and it is just not net mass flow rate, but it is net mass flow rate out, since n is the outward normal. Okay. So, that is how we interpret this integral rho V dot n dA. Just quickly to summarize, V dot n is a normal component of velocity, velocity is volumetric flux. So, V dot n is volumetric flux accounting for that normal component, multiply by rho you get mass flux, multiply by area you get mass flow rate. So, always keep remember that this quantity, the integral quantity represents mass flow rate, very well known quantity to you from your process calculation, much more general than what you know. Okay. And it is net mass flow rate leaving the control volume through the control surface or leaving out of the control volume, because n by convention is outward normal. Okay. So, that is the way of interpreting this integral. Moment you look at the integral, it may be difficult to understand, but if you interpret in this way, it becomes very easy to understand. Okay. Now, let us continue to simplify the integral total mass balance equation. This is where we left. We said we write in terms of sum of outlet flow rates minus sum of inlet flow rates and rate of change of mass. Okay. Now, for steady state, okay, if it is a steady state, then this term is 0, there is no change of mass within the control volume. So, I are left out only the second and third terms, the total mass flow leaving, total mass flow entering, okay, becomes further simplified. Okay. Now, we have considered now there are multiple inlets, multiple outlets. Let us say there is only one inlet and one outlet, there are no, let us assume there are no inlets outlets here, one inlet, one outlet, then this term, this equation can be simplified. Let us assume still unsteady state transients can be there. So, we have dm by dt, because there is only one outlet, we represent that as m dot out minus m dot in become equal to 0. Okay. Our equation becomes much simpler if it is one inlet, one outlet, and if this in this control volume, if it is going to operate under a steady state condition, then this is 0, dm by dt, this term is 0. So, m dot out becomes equal to m dot in, very well known observation or very well known fact that if you have one inlet, one outlet, mass flow entering should be equal to mass flow leaving under steady state condition. As usual, if you want to write in terms of densities, velocities, express mass flow rate in terms of the volumetric flow rate, velocity into area multiplied by density. Similarly, for the inflow. So, either you write in terms of mass flow rate or in terms of density, velocity and then area. We already discussed which is more relevant under which condition. Now, one more assumption we will make, usually the density does not vary much between inlet and outlet. Let us say it is a liquid, then rho out and rho in are same. So, if density is constant, this rho out and rho in both are same, we get a simple expression that V out A out equal to V in A in, which is what you would have written as V 1 A 1 equal to V 2 A 2. Okay. So, when we, which is a well known equation, when we say that let us say there is a converging channel like this, and then because area reduces, velocity increases. Okay. It may be a simple statement, but you should know that this statement comes from, should go back from the law of physics, integral mass balance equation, simplify, and then we say that when area reduces, velocity increases. Okay. So, very commonly told statement, but now we are in a position to clearly understand what is the physical principle behind that statement, either in terms of law of physics or in terms of conservation equation. Okay. Now, you would have used mass balance equation in a process calculation course. We will see how the equation which are derived in this course compares with the equation which you would have used in a process calculation course. Okay. How the equation derived here is much more generic than what you would have used in a process calculation course. Okay. Let us write the first equation derived in this course, that is integral total mass balance equation. Okay. Okay. And after a series of simplifications, we wrote the same equation in this form in terms of mass flow rate. Okay. So, this is the original integral mass balance equation. This equation after a few simplifications in terms of mass and mass flow rates. Now, let us write down the equation which you would have used in a process calculation course. Let us see how do they compare. This equation is where you would have started saying that rate of accumulation of mass is equal to rate of mass in minus rate of mass out. This equation, if you express in terms of variables we have used, rate of accumulation of mass is dm by dt, rate of mass in is m dot I, but I allow for several inlets and inlets. So, I sum from I equal to 1 to number of inlets minus rate of mass out, once again allow for several outlets, I sum from 1 to number of outlets, in terms of our nomenclature is mi dot. Let us compare this equation and then this equation, both are exactly same. The way in which I have written is, or we have written in this course, is that dm by dt, we are always expressing this net rate of flow leaving the control volume. So, that is why we have sum of outlet flow rates minus sum of inlet flow rates. The way in which you would have written in a process calculation course is, rate of accumulation of mass is equal to, you took the flow rates to right hand side. So, they became rate of mass in minus rate of mass out. So, on the right hand side they are sum of flow rates in minus sum of flow rates out, but both are eventually same, only difference is that you have these terms on the right hand side, we have these terms on the left hand side. Otherwise, there is no difference between this equation and this equation. The simplified equation what you have derived and the equation what you would have used. In a process calculation course, usually you deal with processes under steady state conditions. So, the left hand side is 0 and you have terms only on the right hand side, which account for the mass flow in and mass flow out. So, that is how it compares, that is a comparison between the equation used in the process calculation course. This is a equation which you would have used several times in the process calculation course, and this equation. Now, what we will see is how does the equation which you have used, what you have shown is the equation which I used is a equivalent to the simplified form. What we will now do is, how does the equation simplified form used in the process calculation course compare with the most general form of conservation equation which you have derived. Okay. This is the equation used in the process calculation course. What we have derived is a more general form. In what way is it general? Okay. First, transient or unsteady state term, which is not a very major difference, because probably would have even solved some problems with transient. So, I would not say major distinction, but still most of the problems have steady state, but so we are accounting for the transient mass balance also, number 1. Now, next, in the case of process calculation course, you would have allowed for well defined inlets and outlets. Now, because of the surface integral, I allow for any part of the surface to behave as inlet and outlet. So, because of taking a surface integral over any over the surface area, account for inflow and outflow across any part of the control surface, that way more generic. Okay. Now, you would have worked out only in terms of mostly mass flow rate, you would not have worked mostly in terms of even velocities, etc. Now, we are working in terms of velocities, densities, etc. Not alone that, we allow for any angle between this phase and the velocity. So, because we talk in terms of v dot n, the normal component of velocity, any angle between velocity and normal to the surface is taken into account. And thirdly, we also account for density and velocity variation across the surface. Across this surface, density and velocity, that is why they are inside the integral sign. Density and velocity can vary across the surface. So, to conclude this comparison, the equation what I used is nothing but integral mass balance equation, number 1. That equation has come after several simplifications from the original equation which we derived, number 2. Number 3, comparing the original equation what you derived, the most generic equation and the equation which you have used, there are several generalities in the equation which you have derived. What you have seen as a small subset of that under several certain limiting conditions, and how far we are more generic, the transient or unsteady state term, inflow outflow across any surface, any angle between velocity and normal to the surface, and density velocity variation across surface can be considered.